Have you ever wondered how a tiny project, maybe running on just one computer, can explode into something that serves millions of people all over the world? It's one of the biggest challenges on the internet, and today we're going to pull back the curtain on the brilliant, elegant patterns that make it all work.
Our story kicks off way back in 2003 with a site called Delicious. The idea was super simple, but honestly, kind of genius. A social bookmarking site. You could save your links and get to them from any computer, anywhere. And it all started, literally, on a single laptop.
And guess what? People loved it. It got popular. I mean, really, really popular. So that's the real question, isn't it? How do you go from one laptop in a dorm room to a massive system that can handle the whole world logging on at once, without the whole thing just, falling apart? Okay, so before you can worry about millions of users, you have a much more basic problem. Your website exists, but how does anyone on the entire planet find it? Think about it. When you type a website name into your browser, you're trying to find one specific computer among billions. But the internet doesn't really speak in human names. It speaks in numbers, IP addresses. So how does your browser translate that friendly name into the right number? Well, the answer is something called the DNS, or Domain Name System. And you can think of it as basically the entire internet's phone book. When you get a domain name, you're creating an entry in this giant phone book that says, hey, this name points to this specific IP address. It's a huge global system that lets every browser in the world look up your site and connect to the right machine. All right, so thanks to DNS, people can find us. We're on the map. But getting found is just the first hurdle. The moment you get your first users, you run smack into the next big problem: how to actually stay online. See, if your whole website lives on one machine, that machine is what we call a single point of failure. You need to install a security update and restart, boom, the entire site goes down. The hard drive fails? Yep, site's down again. For a service that people are starting to rely on, that's just not going to work. The solution here is a concept called high availability. It's pretty cool. Instead of one server, you run a bunch of them, all with the exact same code. Then, you put another special server out front called a load balancer. Its whole job is to act like a traffic cop, directing incoming users to the different servers. And here's the clever part. It's constantly running health checks, basically pinging each server to make sure it's okay. If one needs to restart, the load balancer sees it's offline and just stops sending people there. For the user, it's seamless, no downtime. So our site is easy to find and it's super reliable. We're golden, right? Well, not quite. As Delicious got more and more popular, it started to hit a very real, very physical wall. 200 megabytes. That's how much new data, new bookmarks from users the site was adding every single day. Now, that might not sound like a crazy amount today, but you got to remember, we're talking about the year 2004. Back then, a decent server might have a 40-gigabyte hard drive. At 200 megs a day, you'd fill that entire drive up in just over 6 months. You are literally, physically running out of space. The only way forward is to split the data across more than one machine. And there's a name for this process. It's called sharding. You take your one enormous database and you slice it up into smaller, more manageable pieces called shards. And for a site like Delicious.us, the most logical way to do this was by user ID. It just makes sense, right? Keep all of one person's stuff together on the same server. So, sharding sounds pretty straightforward, but how you actually do that splitting is absolutely critical. Because the most obvious, most intuitive way to do it, well, it leads to a complete and utter disaster. So here's a simple approach. You take a user's ID, you use a little math trick called the modulo operator, which is just a fancy way of saying the remainder after you divide. And the remainder tells you which server their data lives on. If you have 4 servers and a user ID is 10, the remainder is 2, so they go on server number 2. It's simple, it's clean, and it spreads the users out pretty evenly. What could possibly go wrong? Well, your site is a hit. The traffic is growing. You need to add more capacity. So you buy a 5th server to handle the load. What happens to your simple little formula now? Absolute chaos. That's what happens. Because the number you're dividing by just changed from 4 to 5, the remainder for almost every single user is now different. User 10, who is on server 2, now belongs on server 0. This means you have to physically move almost everybody's data to a brand new machine all at once. It's a catastrophic failure, a total system meltdown. Okay, so the simple formula is a trap. We need a smarter way to shard our data, a way that lets us add or remove servers without causing a complete meltdown.
And this brings us to one of the most elegant and beautiful ideas in all of system design: consistent hashing. Instead of a simple formula, consistent hashing uses a visual, spatial approach. Just picture a circle, like a clock. We use a special function to place each of our servers at different points around the edge of this ring. Then we do the same thing for every user ID. To figure out where a user's data belongs, you just find their spot on the ring and travel clockwise until you hit the very first server. That's its home. Now, this design is way better, but there's still a hidden danger. Look what happens if a server fails. Let's say node 2 goes down. All of the users that belong to it now get reassigned to the next server they hit going clockwise, which is node 5. Suddenly, node 5 has to handle all of its own traffic plus all of node 2's traffic. It's getting double the load. This could overwhelm node 5, causing it to fail, which then triples the load on the next server. You see the problem? It's a domino effect called a cascading failure.
And the solution to that problem is just as clever. It's called virtual nodes. Instead of placing each server on the ring just once, we create multiple virtual copies of each server and scatter them all around the ring. So you might see server A, then server B, then another server A, then server C, and so on.
And you can just see the difference this makes. On the left, when a server fails, its one neighbor gets totally hammered with all the extra traffic. But on the right, with virtual nodes, if all of the A nodes go down, their load doesn't get dumped on one poor server. Nope, it gets reassigned to all their various clockwise neighbors, which are a mix of Bs, Cs, and Ds. The extra load gets spread thinly and evenly across the whole system. No one server gets overwhelmed. It's beautiful. So let's zoom out for a second. We've gone all the way from one laptop to a super resilient distributed system that can grow and shrink without falling over. Let's do a quick recap of the core patterns we just learned.
These are the absolute building blocks of what we call high-level system design. This is the blueprint for almost every large-scale website. First, we used DNS, the Internet's address book, just so people could find us. Then, we used a load balancer to make sure we stayed online, to get high availability. Then came sharding, because we literally ran out of physical space. And finally, the really elegant pattern of consistent hashing, which let us scale that sharded system without blowing everything up. Each one solves a very specific problem that you only run into when you start to succeed.
And this is the thing. From your social media feed to the shows you stream at night, the entire internet you use every day is built on top of these exact same foundational ideas. They're the invisible architecture of our digital world, all of them elegant solutions born from really painful problems. So it makes you wonder, right? As our demand for data and speed just keeps accelerating, what's the next breaking point? What's the next big problem we're going to have to solve, and what will its elegant solution look like?